Hello everyone, today we'll talk about the problem score after flipping matrix. We're given a binary matrix, so a matrix containing zeros and ones. We will interpret every row of that matrix as a binary number, and we want to make the sum of those binary numbers as big as possible. Now, in order to actually maximize it, we have to make some changes to the matrix, and what we're allowed to do is to simply select a row or column as many times as we want, and flip all the bits in that row or column. So all ones turn to zeros, all zeros turn to ones at the same time. So we want to maximize the sum of those numbers interpreted as rows. And the first thing that we'll have to notice is that since this is a binary matrix, since those numbers are written in binary, then we know that if we have a number that starts with a 1 and has something here, and another that also has something here, but it has a 0 here, and of course there are all zeros over there, then this number is greater than this number. Since even if this number had only zeros, and this number had only ones, then this number would be exactly this minus 1. This is how the binary system works. Of course, we assume that there are the same number of digits in both those numbers. So in other words, if you want to maximize the number written in binary, then above all else you want to maximize its most significant digit. If the length is constant, and of course the length is constant because we have a rectangular matrix. And only after you make sure that the first bit is set, if possible, then you go to all the other bits. Luckily for us, here in this problem, we can always make sure that every number has a 1 at the beginning. For example, if we have this matrix, then either we can leave all the ones alone and flip all the zeros, right? So those will be flips. And then those rows will be flipped. The first column is all ones. Another way to do so would be to make sure that the first column is all zeros, and then flip that first column so that all of them are equal to ones. Okay, so that will show us what part of the optimal solution is, but it doesn't give us the optimal solution already. So let's think about all those operations that we can do, what properties they have. And for instance, one thing that we can notice is that if we do some flips of rows and columns, then first of all, every row or column can be flipped either 0 times or 1 time. Since if we flip the same column or row twice, it's the same thing as if we didn't do anything. That happens even if there are some other flips along the way, because order doesn't matter. Since one easy way to see that the order doesn't matter is that if you look at the one particular position, then it just cares about its column, its row, how many times they were flipped, the parity of number of times. So if they were flipped an odd number of times or an even number of times. But it doesn't care about when it happened, because its value is the initial value, and if all the flips of the column and row were in total odd number of times, then the final value will be different than the original one. If we had an even number of flips, perhaps 0 flips, then the value will be the same as in the beginning. So order doesn't matter. And so another thing that we can notice about these operations is that we might, for instance, come up with the idea of, okay, let's make sure that there are all ones at the beginning. And what do we do next? Well, now, if we have all ones in the first column, and we did that by flipping rows, then for every other column, right, so for all those columns, they are in exactly one of two states, because they are either in a given state or in a state after a single flip of that column. That's because this exact state would be either here for every one, we get the original value, so here we have original values, and here we have flipped values. So that would be in the situation if we leave all the ones in the first column alone and turn zeros into ones by flipping rows. And if we did the other way around, so we turned ones into zeros, then those will be flipped and those will be the same, right? But either way, those two positions, so assuming this is the same column, they're also available for us by just flipping that column. So after we, for instance, by operations on rows, make the first column all ones, then all the other columns are in one of two positions. And then which of those positions is better? Well, it's very simple. We want the position that has more ones than zeros. So maybe they have the same number of ones and zeros, and then we don't care. But if, for instance, we have in a column something like this, then this is what we want. If we have something like this is not what we want. We want to flip, because then we get more ones. Since every one at a given position, a given column, will add 2 to the appropriate power to our result. So this gives us a greedy algorithm. The first step would be to flip the first column so that the most significant bits are all equal to 1. And then for every column that we can improve, we can also improve it again. We don't want to do anything with the rows. That's because then we will destroy the first column and it will always be worse than if the first column had a 1 inside it. And also, this includes the solution where, so it leads to the final state that is at least as good as the other solution where we started with all zeros, flipped the first column and then did everything else in the same way. Because then we flip exactly those same remaining columns that we didn't flip originally, right? So if we have a solution that flips rows to make the first column equal to ones, and then flips some other columns to maximize the sum, and somebody else starts by making the first column equal to 0 and flipping it, then which rows did he flip? Well, exactly not those that we flipped in our solution. So all the columns are just in the flipped configuration. So again, we can just flip all those columns that we didn't flip in our original solution. So as we can see, since the order doesn't matter, and since after setting up the first column, then essentially we know everything else that is necessary, then there aren't really many ways to get different good results. And in that case, our greedy will indeed be the best solution. And of course we can do all those things, just make those flips. So whenever we flip in the first column a 0, we flip the whole row, and then we go through all the columns and maybe we flip them. We actually don't have to do that, because we can just go through all the columns from the least significant bit first. And now it has some value, position at row and column has some value. And it also, we can already tell if it is that value or if it's flipped, because if the 0th column, the most significant column, has a 0, then we know that we want to flip that row. And so we can just XOR it by that, because this is essentially, if this is a 1, then we take this thing as what it is, because we don't flip it. If this is a 0, then we have to flip it, so we have to flip this one. But it's easy to just utilize the single XOR operator to do that. If you're unfamiliar with XOR, of course, this is like 1, 1 gives 0, 0, 0 gives 0, otherwise we get ones. So this is the parity of the number of ones in the input. This is the XOR. So this is nice when you want to flip something based on something else. So you can just think of it just as XOR in it. But if you write it as an if, then it's also okay. And here we count the number of zeros. So position RC is a 0 after we flip the first column if XOR of it was a 1 before and the first element is a 1. So we count all the number of zeros, and we either take zeros or we take the height of the matrix minus 0, so that is what we can get in the first column. And first we just add it multiplied by 1, which is 2 to the power of 0. Then, after every step, we multiply our power by 2. So first we added the column that's least significant, we add multiplied by 1, the second column from the back by 2, by 4, and so on. At the end we reach the column that's at the beginning, and we add just all of those times the highest power that we had, because we know that we can guarantee it to be all ones, and this is exactly what we do. So this is a way to do that without modifying the input array or create another input array, because as you can see, as I mentioned before, all the number of possibilities is actually pretty small. And so this is the greedy algorithm that gives us the optimal result. I also explained how you can think about and, let's say, try to prove why it's optimal, just by comparing it to what else you can do and looking at all the other columns that they are essentially in two different states. And if you of those states, then this will be the result this will be exactly the same result that we got in our algorithm.